Most people who click on a video about how cold space is expect to learn about freezing, about ice, about temperatures that would shatter metal in seconds. That part is true, but it is not the part that should concern you. If you were thrown into open space right now without a suit, you would not freeze. You might actually overheat first. The cold of space is not the immediate threat. It is too slow. What ends you in the first 15 seconds has nothing to do with temperature. The temperature of space is minus 454.8 degrees Fahrenheit, less than 5 degrees above the absolute lowest temperature that can physically exist anywhere in the universe. The entire temperature range in which liquid water exists, the range that supports all life on Earth, spans 180 degrees Fahrenheit. The gap between deep space and the lowest temperature physics allows is less than 5. Space is almost as cold as the universe will ever get. In this episode, we cover what minus 454 degrees Fahrenheit really means, where it comes from, what it destroys, and why the universe is still getting colder right now. Temperature measures how fast particles are moving. Hot means fast, cold means slow. At absolute zero, minus 459.67 degrees Fahrenheit, particles would stop moving entirely. That is the floor, the lowest temperature that can exist. Nothing in the universe has ever quite reached it. Space sits at 2.725 Kelvin, minus 454.8 degrees Fahrenheit. That is 4.85 degrees above absolute zero. To put that in perspective, the entire temperature range in which liquid water exists, the range that supports all life on Earth, spans 180 degrees Fahrenheit. The gap between deep space and absolute zero is less than 5 degrees. This is not the cold of winter. It is not the cold of any place on Earth or any place in the solar system. It is the baseline condition of the cosmos, the temperature the universe settles at when nothing else is interfering. The universe is almost as cold as it can possibly be, and it is still getting colder. That minus 454.8 degrees is not just a void. It has a source, and the source is one of the most remarkable accidental discoveries in the history of science. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were using a large horn-shaped antenna in New Jersey, originally built for satellite communications. They were trying to map faint radio signals from the Milky Way, but there was a problem. An irritating, persistent hiss coming equally from every direction in the sky. It didn't matter where they pointed, the signal was always the same. They checked the equipment, they checked for interference from New York City. They ruled that out. They discovered a pair of pigeons had been nesting inside the antenna, coating the inside with droppings. They removed the pigeons, they cleaned the antenna, the noise was still there. What Penzias and Wilson had been trying to eliminate was the cosmic microwave background, the faint, cold afterglow of the Big Bang itself. Light that had been traveling freely through the universe since it was 380,000 years old. Over 13.8 billion years of cosmic expansion, that light had cooled from a roaring fireball of billions of degrees into a whisper of microwave radiation barely above absolute zero. That ancient light fills every cubic centimeter of the observable universe. It permeates everything. It is the reason space has a temperature at all, and it corresponds exactly to minus 454.8 degrees Fahrenheit. Penzias and Wilson won the Nobel Prize for finding it by accident while looking for something else. That minus 454.8 degrees is not fixed. It is a snapshot. As the universe continues to expand, the cosmic microwave background radiation stretches into ever longer wavelengths and continues to cool. The universe today is colder than it was a billion years ago. It will be colder still a billion years from now. Every moment, the baseline temperature of the cosmos drops fractionally closer to absolute zero. This cooling has a name and an endpoint. Physicists call it the heat death, the state the universe is moving toward in which every temperature gradient is equalized, every star has burned out, every black hole is evaporated, and the cosmos settles into a final, frozen equilibrium from which nothing can ever emerge again. No energy difference, no chemistry, no motion. Current estimates place that endpoint at around 10 to the power of 100 years in the future, a 1 followed by 100 zeros. The The current age of the universe has 11 digits. That number has 101. The direction, however, is unambiguous. Everything is cooling. Everything is heading toward the cold. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. The background temperature of the universe is not the coldest thing in space. Because the cosmic microwave background fills all of space, any object sitting in open space absorbs some of that radiation. Objects in open, deep space don't reach absolute zero. They settle at roughly the background temperature, bathed in that ancient light from all directions. But there are places in the universe that are colder than even that. The Boomerang Nebula is a young planetary nebula approximately 5,000 light-years from Earth. It has been measured at 1 Kelvin, minus 457 degrees Fahrenheit, 1 degree above absolute zero, colder than the cosmic background itself. How is this possible? The dying star at its center is expelling gas outward at high speed. When gas expands rapidly, it cools. The same principle that makes an aerosol can feel cold when you spray it. The gas in the Boomerang Nebula is expanding so violently that it drops below even the ambient temperature of the cosmos around it. It is the coldest known natural object in the observable universe. Numbers on a scale don't reveal what cold actually does. The physics does. At room temperature, metals are solid, but their atoms are in constant vibration. The crystal structure is flexible enough that metals can be bent, hammered, drawn into wires. Apply stress to a warm piece of steel and it deforms, gradually, with warning before it finally breaks. This property is called ductility. Cool that same metal far enough and everything changes. The vibrations that give metals their flexibility slow and diminish. The crystal structure becomes rigid in a way it isn't at room temperature. Apply stress to ultra-cold metal and instead of bending, it shatters. Clean fractures, sudden, no deformation, no warning. This is called the ductile to brittle transition, and it is not a minor engineering footnote. Metallurgical analysis of steel recovered from the Titanic wreck showed that the steel used in the ship's hull had high sulfur content, making it unusually brittle at cold water temperatures. The water temperature in the North Atlantic on the night of April 14, 1912, was just below freezing. When the hull struck the iceberg, the steel didn't dent, it fractured. Seams opened instead of bending. Cold changed what the material was and changed the outcome of that night. At the temperatures of deep space, approaching minus 450 degrees Fahrenheit, this transformation is total. Rubber seals shatter like pottery. Lubricants solidify or become so viscous they might as well be solid. Gases we encounter as gases on Earth freeze into rock. On Pluto, nitrogen is ice, methane is ice, carbon monoxide is ice. Things we breathe are rock on another world. The human body maintains its core temperature within an extraordinarily narrow range to function, roughly 94 to 107 degrees Fahrenheit. Below 94 degrees, hypothermia begins to impair judgment. Below 82 degrees, the heart starts to develop life-threatening arrhythmias. Above 107 degrees, proteins unfold and cells begin to die. A span of 13 degrees between life and breakdown in either direction. Against the full temperature range of the universe, from billions of degrees inside neutron stars to the minus 454.8 of deep space, 13 degrees is nearly nothing. A sliver so thin it barely registers. If a human body were exposed to open space, the cold would not be the immediate threat. This is one of the most persistent misconceptions about space. The near vacuum is paradoxically an extraordinary thermal insulator, with almost nothing to conduct heat away from the body. Radiation alone would cool it slowly. What would kill first is the vacuum itself. Gases dissolved in the blood would form bubbles. Moisture on exposed surfaces would vaporize instantly. And without oxygen reaching the brain, consciousness would be gone within about 15 seconds. The cold is the long-term condition, the relentless, patient drain of warmth through radiation over hours and days. For spacecraft, this is the engineering reality. Not a dramatic freeze, but a slow, continuous thermal challenge requiring constant management. Spacecraft engineers don't think about dramatic freezes, they think about heat budgets. In Earth orbit, the International Space Station swings between sunlight and shadow every 90 minutes. The sunlit side of the station reaches around plus 250 degrees Fahrenheit. The shadowed side at that exact same moment sits at around minus 250 degrees Fahrenheit, a difference of 500 degrees across the same structure at the same instant. There is no atmosphere to equalize temperatures. Whatever the sun hits gets hot. Whatever the sun doesn't hit gets cold. The ISS has an elaborate thermal control system, large radiator panels, multi-layer insulating blankets, fluid loops circulating ammonia coolant, working continuously to keep the interior at a livable temperature despite the wild temperatures happening centimeters outside the hull. Missions to the outer solar system face a different problem. At Neptune's distance, the sun delivers about 900 times less energy per square meter than it does at Earth's orbit. Solar panels become useless. The Voyager probes, Cassini, New Horizons all relied on nuclear power sources called radioisotope thermoelectric generators. These devices convert heat from the slow radioactive decay of plutonium-238 into electricity. They also provide a safety source of warmth to prevent the spacecraft from cooling to the point of failure. A few kilograms of radioactive material providing a nuclear campfire, keeping instruments alive in the dark at the edge of the solar system. Temperature across the solar system is not a simple gradient from hot at the center to cold at the edges. It is far more varied than that. Mercury, the closest planet to the Sun, reaches plus 800 degrees Fahrenheit in daylight. At night, with no atmosphere to hold that heat, the same surface drops to minus 290 degrees Fahrenheit, a swing of over 1,000 degrees between day and night on a single planet. Mars, which orbits 3 times farther from the Sun, is actually warmer at the poles than Mercury is in the dark. At the cloud tops of Neptune, the farthest official planet, temperatures fall to minus 393 degrees Fahrenheit. Pluto, orbiting in the Kuiper Belt, reaches surface temperatures between minus 375 and minus 400 degrees Fahrenheit. When the New Horizons spacecraft flew past in 2015, it found not a dead featureless rock but nitrogen ice plains, mountains of water ice miles high, and a layered haze. At those temperatures, the things we call gases become rock. Nitrogen, methane, carbon monoxide, all frozen solid on the ground. And then, beyond the heliopause, the boundary where the sun's influence ends and true interstellar space begins, roughly 11 billion miles out, the temperature drops to that cosmic baseline, minus 454.8 degrees Fahrenheit. The Voyager 1 probe crossed that boundary in 2012. It is still transmitting. Here is something that almost never gets said about the cold of space. Life on Earth does not run on heat. It runs on the difference between heat and cold. Without cold, without somewhere for energy to flow toward, the sun's warmth would be useless. Temperature differences would flatten. Chemistry would stop. There would be nowhere for energy to go. Every calorie powering every living thing on Earth is ultimately derived not from the sun's heat alone, but from the contrast between the heat and the minus 454.8 degrees that the surrounding void offers as a sink. The cold of space is what makes the sun's energy meaningful. Remove it, and nothing happens. The cold of space is not separate from the story of life. It is part of the engine. And there is one more layer to this that goes even further. In the vast, dark molecular clouds scattered throughout the galaxy, regions where temperatures hover near 1 Kelvin, chemistry does not stop. It transforms. At those temperatures, quantum mechanical tunneling takes over, allowing reactions on the surfaces of tiny dust grains that would be impossible in warmer environments. Astronomers have detected in these cold clouds molecules of surprising complexity: simple sugars, formic acid, methanol, ethanol. From the Rosetta mission, which orbited and landed on a comet in 2014, scientists detected glycine in the outgassing material, an amino acid, one of the 20 building blocks of every protein in every living organism on Earth, preserved in frozen comet ice for 4.5 billion years, formed in all likelihood in the cold between stars before our solar system existed. The ingredients that made life possible on Earth may have been assembled not in the heat of a star, but in the cold between them. The temperature of space is not a curiosity. It is a fact about where the universe is and where it is going. We live in what is, cosmologically speaking, a warm period, a brief luminous phase between the fiery beginning and the cold, dark, silent end. The stars that light our sky are temporary. The warmth we feel is borrowed. Every temperature difference in the cosmos is being consumed by stars burning their fuel, by heat diffusing into the cold, by the second law of thermodynamics doing what it always does. The universe began near the Planck temperature, a number so large that our mathematics breaks down trying to describe it. It has been cooling every moment since. 13.5 billion years of cooling have brought it to minus 454.8 degrees. The journey toward absolute zero continues. Everything is moving in one direction. We exist because of a temperature gradient, because the sun is hot and space is cold, and between those two extremes, chemistry found a way to organize itself into something that could notice. The coldest space is not the backdrop to the story. It is part of the story. Now you know how cold space is. But there's a question most people never think to ask. If space is this cold, why isn't it getting any warmer with 2 trillion galaxies and billions of stars burning in every direction? Watch Why is Space So Cold When the Sun and Billions of Stars Are So Hot to find out.